Take a moment. Look at your hand right now. Notice how solid it feels, how real it is. You can feel the warmth of your skin, the texture of your fingers. But what if I told you something extraordinary? What if everything around you, your hand, this room, the stars in the night sky, might actually be a kind of projection? Not in some mystical or philosophical way, but in a very real, physical sense. Back in 1997, a young physicist named Juan Maldacena discovered something that seemed impossible. His mathematics suggested that our entire three-dimensional world, with all its depth and texture, could be like a hologram. You know those 3D images on credit cards? They look three-dimensional, but they're really just flat surfaces creating an illusion. What if our universe works the same way? Most scientists at the time thought this was just an interesting mathematical trick, something neat on paper, but not connected to reality. Then something unexpected happened. Evidence started appearing. Real evidence from multiple directions, all pointing to the same stunning conclusion. Could it be that you and I, along with everything we've ever known, exist as information painted on a distant two-dimensional surface? Could the depth and substance of reality itself be an illusion? Today, we're going to explore this idea together. We'll look at the evidence, hear from the scientists making these discoveries, and gently work our way through what might be one of the most profound revelations in human history. Take a breath. Let's begin this journey together.
Our story begins in the 1970s with Stephen Hawking working at Cambridge University in England. Hawking was fascinated by black holes, those mysterious regions in space where gravity becomes so powerful that nothing, not even light, can escape. Einstein's equations predicted they should exist, and astronomers were starting to find them out in the cosmos. But nobody really understood what happened at a black hole. It was one of the great mysteries of physics. Then, Hawking made an incredible discovery. He found that black holes aren't completely black after all. Through a subtle quantum process happening right at the edge, the event horizon, black holes actually glow. Very faintly, but they glow. This became known as Hawking radiation. Here's where things got troubling. If black holes radiate energy, they slowly shrink. Eventually, over trillions upon trillions of years, they disappear completely. And when they vanish, they take everything that ever fell inside with them. This created a huge problem. You see, there's a fundamental rule in physics, one of the bedrock principles we build everything on. Information cannot be destroyed, ever. Think of it this way. If you burn a book, the book is gone, but the information isn't technically destroyed. It's scrambled into heat and light and ash. With enough knowledge, you could theoretically piece together what the book said. The information still exists somewhere in the universe. But with black holes? If Hawking was right, the information just vanished completely. Gone from the universe forever. For 20 years, this paradox haunted physicists. It kept them up at night. How could the universe allow information to be destroyed? Every solution anyone proposed seemed to create new problems. Then, in 1993, a Dutch physicist named Gerard 't Hooft noticed something strange.
't Hooft was studying the mathematics of black holes when he spotted something odd, something that didn't quite make sense. When you calculate how much information a black hole can hold, you'd naturally expect it to depend on the volume, how much space is inside the black hole. That's how it works with everything else, right? A bigger box holds more stuff. But the equations said something different. The information a black hole can contain depends on its surface area, not its volume, just the area of its outer boundary. Imagine a sphere the size of Earth. Common sense tells you that the amount of information you could pack inside should depend on all that space inside the sphere. But Toft's calculations suggested otherwise. What mattered was just the surface, like everything was written on the outside skin of a balloon. Let that sink in for a moment. If true, it would mean that one of our dimensions of space, the depth, the volume we experience, might be redundant, unnecessary, perhaps even an illusion. Toft called this the holographic principle, the idea that our three-dimensional world could be completely described by information encoded on a two-dimensional surface, much like a hologram projects a 3D image from a flat surface. Around the same time, Leonard Susskind at Stanford University independently arrived at the same conclusion. Two brilliant minds working separately, finding the same strange truth hidden in the equations. Most physicists found it interesting, even beautiful, but they assumed it was just a quirk of black hole physics, a mathematical curiosity, not a description of actual reality. They were about to be proven wrong. In late 1997, Juan Maldacena was working at Harvard. He was only 29 years old, exploring the complex mathematics of string theory. String theory, if you're not familiar, is an attempt to explain everything in the universe by proposing that the smallest particles aren't really particles at all. They're tiny vibrating strings of energy. Maldacena was playing with the mathematics when he stumbled onto something extraordinary. He found a precise connection between two completely different universes. Not real universes, but mathematical models physicists use to understand reality. On one side of his equation was a five-dimensional universe. Imagine our normal 3 dimensions of space plus time plus one more spatial dimension we can't perceive. This universe contained gravity, black holes, all the complexity we see in our cosmos. On the other side was a 4-dimensional flat boundary surrounding that universe. This boundary had no gravity at all, just particles interacting according to simpler quantum rules. Here's the remarkable part. Maldacena proved these two descriptions were completely equivalent, identical. Every single event happening in the 5-dimensional universe with gravity could be perfectly translated into the language of the 4-dimensional boundary without gravity. The interior universe was a hologram of the boundary. Think of it like this. Imagine a snow globe. The 3-dimensional scene inside the globe could be entirely described by information encoded on the flat glass surface. Two completely different ways of describing the same reality. Within months, physicists around the world were using Maldacena's discovery. Problems that had been impossible to solve for decades could suddenly be worked out by translating them to the simpler holographic boundary. His paper became the most cited work in theoretical physics, not just because it was elegant, though it certainly was, but because it provided the first rigorous mathematical proof that the holographic principle was real. It wasn't philosophy anymore. It was mathematics. It was physics. But this raised an unsettling question that nobody could ignore. If Maldasena's mathematical universe could be holographic, what about ours? What about the universe we actually live in? The possibility seemed almost too strange to consider, but scientists are driven by evidence, not comfort, and the evidence was about to start piling up. In 1981, physicist Jacob Bekenstein calculated something fascinating. He wanted to know, what's the maximum amount of information that can fit in any region of space? You might think there's no limit, just keep adding information until you've filled every atom, every particle, every tiny bit of space. But Bekenstein found something different. There is a limit, and it's determined not by the volume of the region, but by its surface area. The calculation involves incredibly small units called Planck lengths, the smallest meaningful distance in physics, about 1 billion times smaller than an atom. The maximum information equals the surface area, measured in these tiny Planck squares, divided by 4. For something the size of your head, this limit works out to about 10 with 67 zeros after it, a number so large it's hard to even imagine. That's vastly more than all the information in every atom in your brain. But here's what matters. The limit exists, and it depends on surface area, not volume. If information were truly three-dimensional, if volume really mattered fundamentally, there wouldn't be this kind of limit. The fact that it exists and that it's tied to surface area hints at something profound. Maybe the third dimension isn't as fundamental as we think. Maybe reality really is two-dimensional at its core, and the depth we experience emerges from how that information is organized. In 2013, physicists made a discovery that sounds almost like science fiction. Mark van Raamsdonk and Brian Swingle were studying quantum entanglement. That's the strange phenomenon where two particles become mysteriously connected. When you measure one, you instantly know something about the other, even if they're on opposite sides of the universe. Einstein famously called it spooky action at a distance, and it's one of the weirdest confirmed facts about our universe. Van Raamsdonk and Swingle used Maldasena's holographic mathematics to show something remarkable. Quantum entanglement between particles on the holographic boundary actually creates space in the interior universe. Let me say that again more slowly. The empty space between objects, the distances we measure, the gaps we cross, might not be fundamental. Space itself could emerge from patterns of quantum entanglement. When particles on the boundary become entangled, space forms in the interior. When that entanglement breaks, space tears apart. Two researchers named Shinsei Ryu and Tadashi Takayanagi even developed an equation, now called the Ryu-Takayanagi formula, that precisely calculates how much space is created by specific entanglement patterns. This has been tested mathematically in countless scenarios. It works every time. What this suggests is almost overwhelming. The stage where physics happens, the arena of space itself, isn't fundamental. It's emergent. It arises from something deeper, from information relationships we can't directly see.
Sometimes unexpected discoveries come from unexpected places. In 2008, scientists at the GEO 600 gravitational wave detector in Germany noticed something odd. This instrument is designed to detect ripples in the fabric of space-time created by colliding black holes or neutron stars. But they were picking up noise. Not random static, but a specific kind of noise at a particular frequency that shouldn't be there. Craig Hogan, director of the Fermilab Center for Particle Astrophysics, proposed a startling explanation. Maybe, he suggested, they were detecting holographic noise. Here's the idea. If we live in a hologram, space-time can't be perfectly smooth at the smallest scales. It would have to be made of discrete units, like pixels on a screen. And GEO 600 was sensitive enough, measuring distances thousands of times smaller than a proton, that it might be detecting this fundamental graininess. Hogan's team built a special device called the holometer specifically to look for this holographic noise. While the initial results weren't conclusive, they did establish limits. If space-time is pixelated, the pixels are incredibly small, smaller than we can currently measure. What's significant isn't whether they found definitive proof. What's significant is that we've reached a point where we can actually try to measure whether we live in a hologram. We're no longer just theorizing, we're experimenting.
Let's return to black holes for a moment, because they keep teaching us things about reality. Every black hole has a temperature. It's incredibly cold. A black hole the mass of our sun would be just a tiny fraction of a degree above absolute zero, but it has a definite temperature that can be calculated. That temperature is directly related to the black hole's entropy, essentially how much information it contains. And here's the key. Stephen Hawking's equations show that this entropy is proportional to the black hole's surface area. Double the surface area, you double the information capacity. The relationship is exact. This makes perfect sense if black holes are holographic objects. The information isn't stored in the mysterious volume beyond the event horizon. It's encoded on the event horizon itself, on the surface, at exactly 1 bit of information per Planck-sized square. When something falls into a black hole, the information doesn't disappear into some three-dimensional interior. It gets scrambled and spread across the two-dimensional event horizon, like ink spreading across paper. Physicists have verified this relationship for every type of black hole they can model: spinning ones, electrically charged ones, large ones, small ones. The mathematics works perfectly every time. Black holes, the most extreme objects in the entire universe, behave exactly as if they're fundamentally two-dimensional objects, creating the illusion of a three-dimensional interior. And if the most extreme objects in nature work this way, maybe everything does. This is just the beginning. The evidence goes much deeper, touching the very foundation of reality.
In 2014, physicist Ahmed Almhiri made a discovery that changed how we think about the universe. He was studying quantum error correction. Now, this might sound technical, but bear with me. It's actually a beautiful idea. When engineers build quantum computers, they face a problem. Quantum information is fragile. The tiniest disturbance can corrupt it. So they developed clever codes that store information redundantly across multiple quantum bits. Even if some bits get corrupted, you can still recover the original information. Almhiri discovered that Maldasena's holographic correspondence uses exactly the same mathematical structure as these quantum error correction codes. In other words, the universe itself appears to be using the same optimal information protection strategies that our best computer scientists have invented. The three-dimensional interior universe we experience is protected from errors by redundant encoding on the two-dimensional boundary. Information is spread out in such a way that even if large chunks are lost or corrupted, the full three-dimensional description can still be reconstructed. Daniel Harlow and Patrick Hayden proved this mathematically. The dictionary that translates between the boundary and the interior, between the hologram and the projected universe, follows the same rules as the most sophisticated error correction codes known to science. This profoundly changed how physicists think about space-time. It suggests the holographic description isn't just a convenient mathematical tool. It might be closer to the fundamental truth than the three-dimensional universe we directly perceive. The universe, it seems, is processing information the same way our most advanced computers do.
Now we're going to explore something even stranger, something about time itself. In the holographic boundary, the flat surface where the information is encoded, time behaves normally. It marches forward according to straightforward quantum mechanical rules. One moment follows another. But in the interior universe, something remarkable happens. Researchers discovered that time itself emerges from quantum entanglement patterns on the boundary. Think about that. Time, the flow from past to future, the fact that we remember yesterday but not tomorrow, arises from how information is organized on the holographic surface. In 2013, Leonard Susskind and Juan Maldacena demonstrated this explicitly. They showed that creating a wormhole, a tunnel connecting distant points in space in the interior, corresponds to entangling particles on the boundary. the geometry of space-time, including time as a dimension, emerges from quantum information relationships. This means time might not be fundamental. It could be like the wetness of water, a property that emerges when you have lots of molecules together, but isn't possessed by any individual molecule. Time could be something that emerges when you're inside the hologram, experiencing it from within. But at the most fundamental level, at the boundary, time might be just another way of organizing information.
For years, there was a catch. Maldaceno's proof worked for a special kind of universe, one with a negative curvature, curving inward like a saddle. Our universe doesn't curve that way. Observations show our universe is expanding outward in all directions with a positive curvature. So could the holographic principle apply to us? In 2011, physicists Tom Banks and Willy Fischler proposed that it could. They suggested the holographic screen for our universe isn't at some infinite distance, it's at our cosmic horizon. Our cosmic horizon is the boundary of the observable universe, currently sitting about 16 billion light-years away from us. Beyond that boundary, space is expanding so fast that light from those regions can never reach us. We can never see beyond it. Banks and Fischler showed that all the information in our observable universe could be encoded on this cosmic horizon at the same density as black hole horizons, 1 bit per Planck area. Since then, researchers including Eva Silverstein at Stanford and Shi Dong at UC Santa Barbara have developed increasingly detailed versions of cosmological holography. It's not as mathematically complete as Maldaceno's original discovery, but every year the framework gets more solid, more convincing. The holographic principle might not just apply to imaginary mathematical universes. It might apply to the real universe we actually inhabit.
Remember the black hole information paradox we discussed earlier? The problem that haunted physicists for decades? In 2012, a group of 4 physicists, Almhiri, Marov, Polchinski, and Sully, showed the problem was even worse than people thought. They found that black holes seem to violate multiple fundamental principles of physics simultaneously. Either information was destroyed, or Einstein's theory of relativity was wrong in a specific way, or something dramatic happened at the black hole's edge, possibly a firewall of intense radiation that would instantly destroy anything trying to fall in. None of these options were acceptable. Each violated something we knew to be true. The holographic principle offered a way out. If information never really enters the black hole's interior, if it's always encoded on the 2-dimensional horizon, then there's no paradox. The interior space-time, including the smooth horizon that relativity predicts, emerges from the holographic encoding. From inside the black hole, if you could somehow survive falling in, you'd experience a smooth passage through the event horizon, exactly as Einstein predicted. But fundamentally, you never left the 2-dimensional surface. Your 3-dimensional journey through the black hole's interior is a holographic projection.
Recent work by Daniel Harlow at MIT and others has shown this resolution works mathematically. When you properly account for holography, the firewall paradox simply dissolves. The evidence keeps building from every direction, pointing toward the same stunning conclusion. But what does it all mean? What's the big picture?
The holographic principle didn't appear out of nowhere. It grew naturally from string theory, the attempt to unify all of physics by proposing that fundamental particles are actually tiny vibrating strings. In string theory, these strings exist in 10 or 11 dimensions. We only perceive 3 dimensions of space plus time because the extra dimensions are curled up incredibly small, too tiny for us to detect. The holographic correspondence revealed something fascinating about these extra dimensions. At least one of them might not be fundamental at all. It emerges from the holographic encoding. Ed Witten at the Institute for Advanced Study showed that string theory naturally creates holographic universes. The mathematics of strings living on a boundary automatically generates a higher dimensional space-time with gravity emerging naturally. This suggests our experience of 3-dimensional space with all its volume and depth might be similar to how our brains create 3-dimensional vision. Your eyes only receive 2-dimensional images, but your brain processes them to create the perception of depth. The universe might be doing something similar on a cosmic scale, taking 2-dimensional information and creating a 3-dimensional experience.
So, where does the scientific community stand on all this? Today, the majority of theoretical physicists working on quantum gravity accept some form of the holographic principle as likely correct. Gerard 't Hooft, who first proposed the idea, remains convinced. He said, "The holographic principle is not optional. It's a necessity imposed by what we know about black holes." Leonard Susskind goes further. He stated publicly, "I believe we're living in a hologram. The 3-dimensional world we perceive is a projection from information encoded on a distant surface." Juan Maldacena, who discovered the first proof, is more cautious. He notes, "We have rigorous mathematical proof in specific cases. Whether our universe works exactly this way remains an open question, but the principle seems too powerful and universal to be just coincidence." Not everyone agrees, of course. Science thrives on debate. Some researchers pursuing different approaches, like loop quantum gravity, don't naturally incorporate holography. Carlo Rovelli and others suggest space might be fundamentally granular, made of discrete loops rather than holographic. Roger Penrose, the Nobel laureate, has expressed skepticism. He said, "The mathematics is beautiful, but we shouldn't confuse mathematical equivalence with physical reality.
Just because two descriptions are equivalent doesn't mean one is more fundamental than the other. These debates are healthy, they're how science progresses, but the momentum is clearly building toward holography being a real, fundamental aspect of nature.
This forces us to reconsider some very basic assumptions. If we're holograms, what does that mean for consciousness, for the sense of being you? Your thoughts, memories, and sense of self would be encoded in information on the cosmic boundary. Your experience of having a brain and body would be a holographic projection emerging from that encoding. Does the holographic description, the information on the boundary, have its own experience? Or is consciousness itself holographic, emerging from patterns in the information the same way space-time emerges from entanglement? Philosophers and physicists are genuinely grappling with these questions. Some people wonder if holography means we're living in a simulation, like a computer program. The answer seems to be no, not in the traditional sense. There's no external computer running our universe. The holographic boundary is the universe, and we're patterns of information within it. But it does suggest that reality has layers. What we perceive as fundamental might be emergent, and the true fundamental description might be radically different from our everyday experience. It's like discovering that a beautiful tapestry, when you look closely enough, is made of individual threads. The tapestry is real, it exists, but understanding the threads helps you understand the bigger picture.
For decades, holography was purely theoretical. Beautiful mathematics with no way to test it. That's starting to change. The next generation of gravitational wave detectors is being built right now. Upgrades to LIGO and the proposed Einstein telescope will be sensitive enough to potentially detect holographic noise, tiny fluctuations that would appear if space-time is pixelated at the smallest scales. If space-time really is made of discrete units like pixels on a screen, these incredibly sensitive instruments should detect correlated fluctuations in their measurements. The signature would be distinctive and unmistakable. Craig Hogan's team has refined predictions about exactly what holographic noise should look like. They've identified specific patterns and frequencies where the signal should appear. Meanwhile, observations of the cosmic microwave background, the faint glow left over from the Big Bang, might contain evidence. The Planck satellite has already mapped this radiation with extraordinary precision. Some researchers are now analyzing that data, looking for subtle patterns that would indicate a holographic origin. They're looking for correlations between widely separated points in the sky, patterns that shouldn't exist unless information is being processed holographically. We may be just years away from direct observational evidence. Imagine that. We might actually be able to detect that we're living in a hologram. Here's an unexpected twist. Understanding holography might help us build better computers. Researchers at Google, IBM, and universities worldwide are exploring something called holographic quantum error correction. They're using the same mathematical structures that describe the universe to protect quantum information from corruption. In 2023, a team at the University of Maryland successfully built a small-scale device that stores and protects information using holographic quantum codes. It worked exactly as the theory predicted. If this technology can be scaled up, it might enable quantum computers powerful enough for practical applications, designing new medicines, understanding climate systems, solving problems that would take conventional computers longer than the age of the universe. There's a beautiful irony here. By understanding how the universe encodes information holographically, we learn to build better information processors. And those computers might eventually be able to simulate entire universes of their own. Each step forward in technology brings us closer to understanding our own nature. At the deepest level, holography might be the key to something physicists have sought for over a century, a unified theory of everything. For generations, we've had two magnificent but incompatible theories. Quantum mechanics beautifully describes the very small, atoms, particles, the quantum realm. General relativity perfectly describes the very large, planets, stars, the curvature of space-time. But they contradict each other at the deepest level, where both should apply inside black holes at the moment of the Big Bang. The equations break down. The holographic principle might bridge this gap by showing that gravity emerges from quantum information on a boundary with no gravity. The holographic correspondence provides the first concrete example of quantum gravity working mathematically. String theorist Brian Greene has noted holography might be revealing that gravity isn't fundamental. It's an emergent phenomenon, like temperature arising from molecular motion. The fundamental description is quantum information on a boundary. If this is true, it would complete the revolution Einstein started. He showed us that gravity isn't a force pulling objects together. It's the curvature of space-time itself. Holography goes further. Space-time itself isn't fundamental. It emerges from quantum information. Recent work by Leonard Susskind and others on ER equals EPR, the idea that wormholes and quantum entanglement are actually the same thing, builds on holographic insights.
They're showing how the entire fabric of reality might be woven from quantum connections. Other teams are using holography to understand the Big Bang and cosmic inflation. Early results suggest it might explain one of cosmology's deepest mysteries: why the universe began in such an orderly, low-entropy state. Piece by piece, the puzzle is coming together. And at the center of it all is this strange, beautiful idea that we're holograms and reality is information. But this raises questions that go beyond physics into philosophy, consciousness, and the meaning of existence itself.
If holography is correct, we need to rethink what we mean by real. The three-dimensional universe you experience right now is real. It exists. It follows consistent laws. When you touch a table, it's genuinely solid. When you look at the stars, they're truly there. But fundamentally, this three-dimensional reality isn't the deepest layer. It's a derived description emerging from information encoded on a lower dimensional boundary. Here's an analogy that might help. When you watch a movie, the images on screen are real. They exist as patterns of light and shadow. But the fundamental reality is the digital data stored on a disk or server. The movie you experience is a projection of that data. We might be like characters in that movie, unaware that the fundamental description of our existence is written in a different language, on a different level. But here's what makes it even stranger. That boundary isn't somewhere else. It's not a distant cosmic screen we could travel to. In cosmological holography, the boundary is defined by your perspective, your cosmic horizon. Every observer has their own holographic screen. This suggests that observation and information might be more fundamental than physical objects. The universe exists as information. It's processed through observation, and from that processing emerges the consistent three-dimensional experience we all share. Reality is real, but it's also deeper and stranger than it appears. The holographic principle has fascinating connections to the idea of multiple universes. Remember, every observer has their own cosmic horizon, their own boundary of what they can see. This means every observer, in a sense, lives in their own holographic universe. Not separate universes, but different holographic encodings of the same underlying reality. But string theory adds another layer. The mathematics allows for an enormous number of possible configurations, 10 to the power of 500 different ways the extra dimensions could be arranged. Each configuration would produce a universe with different physical laws. If holography is correct, each possibility might correspond to a different boundary theory, different holographic screens encoding different physics. There's also eternal inflation theory, which suggests our Big Bang is just one of infinitely many, each creating a bubble universe. Holography suggests these bubble universes might all be different holographic projections, each with its own boundary. This raises an almost overwhelming possibility. The universe itself might be holographic, an infinite collection of boundaries, each encoding a different possible universe. And somewhere in the mathematics connecting all these boundaries might be the ultimate theory, the fundamental description from which all possible physics emerges. We're not just asking, are we a hologram? We're asking, are all possible universes holographic? This brings us to one of the most profound questions. What about consciousness? What about you? If your body and brain are holographic projections, where does your subjective experience come from? Where is the you that's reading these words right now? One possibility is that consciousness emerges from information patterns the same way space-time does. Your sense of being yourself arises from specific complexity patterns in the holographic encoding. Neuroscientist Christoph Koch, who studies consciousness, has suggested if the universe processes information holographically, consciousness might be an inherent property of certain information patterns. It might not matter whether those patterns are encoded holographically or emerge in the bulk universe. Philosopher David Chalmers notes this might help with what he calls the hard problem of consciousness, explaining how subjective experience arises from physical processes. If physical processes are themselves emergent from information, then consciousness and physics might be two aspects of the same underlying information processing reality. Some researchers are exploring whether quantum entanglement in the brain might connect to the holographic structure of space-time. This remains highly speculative, but it's being seriously investigated. What seems increasingly clear is this: consciousness can't be separated from the holographic nature of reality. We're not external observers looking at a holographic universe from the outside. We're patterns within the hologram itself, observing our own nature. We started with a simple question. What if our three-dimensional reality is a holographic projection? Together, we've journeyed through black hole physics, explored Maldasena's mathematical proof, examined evidence from quantum entanglement to cosmic horizons, and contemplated what it means for consciousness and existence. The evidence has come from multiple independent directions developed by brilliant minds over decades of careful work. The mathematics is rigorous, the logic is sound, the implications are profound. The scientific consensus is building. Some version of the holographic principle is very likely true. The questions now focus on exactly how it applies to our universe and what the deepest implications might be. We've learned that dimensions might emerge rather than being fundamental, that information is more basic than matter or energy, that space itself arises from quantum connections, that the universe processes information using the same optimal strategies we've discovered for quantum computing,
But vast territories remain unexplored. We can't yet test all the predictions. We haven't fully understood cosmological holography. We're still working out what it means for consciousness and free will. What we can say with growing confidence is this: reality is far stranger and more wonderful than we imagined. The solid, three-dimensional universe we experience every day might be a cosmic hologram, shadow and substance intertwined, information and experience inseparable. Look at your hand one more time. It's still there, still warm, still real. The holographic principle doesn't make it less real. It reveals that real is richer and more mysterious than we knew. Somewhere, perhaps encoded on your cosmic horizon, perhaps woven into the fabric of space-time itself, information dances in patterns of quantum states, and from that dance emerges everything: you, me, the stars scattered across the night sky, the vast empty spaces between them. We are the universe becoming aware of itself, holographic patterns achieving consciousness, information awakening to wonder at its own existence. The universe is vast beyond measure, the mysteries are endless, and the journey of discovery continues. Perhaps the most beautiful truth we've uncovered is this: we're part of something far grander than we ever imagined, connected at the deepest level to the universe.
And so, we arrive at the end of our journey. Not at the edge of space, not at the end of time, but at a quiet understanding that the universe is far deeper than it appears, that what feels solid, what feels permanent, may be patterns of information gently unfolding. Yet even if reality is a hologram, even if space and time are projections, your experience is real. Your thoughts are real. Your curiosity is real. Your wonder is real. You are not an illusion. You are a moment of awareness in a universe that has learned how to observe itself. Perhaps that is the most beautiful part of all, that from equations and energy, from silence and space, emerged something that can ask questions, that can feel awe, that can look into the darkness and search for meaning. As the stars continue their slow, silent dance, as galaxies drift through endless night, you can rest now. You don't need to understand everything. You are already part of the answer. So take a slow breath, let your thoughts fade, and allow the universe to carry you. Because the mystery isn't out there, it's within you, and the journey has only just begun.